Hey guys, so my name is Annika and this is chapter 4 of physics, forces and the laws of motion. This chapter is going to include 4 main topics. We have changes in motion, Newton's first law, Newton's second and third laws, and everyday motion. So let's start with changes in motion. We'll start by defining forces. A force is any interaction between an object and its environment. So for example, over here on the left we have a person kicking a ball. The person's foot is exerting a force on the ball as it pushes the ball into the air. Similarly, here on the right we have a person sitting on a chair. The person's weight is exerting force on the chair because it's interacting with the chair as the person sits down. Any force will cause objects to accelerate. For instance, with this example with the ball, the person's foot kicking the ball is giving the ball a velocity as it pushes into the air. This is causing the ball to accelerate. So let's look at units for defining force. The standard unit of force is the Newton, named for the scientist Isaac Newton. A Newton is the amount of force required to accelerate 1 kilogram of mass by 1 meter per second squared. Therefore, the units of force are kilograms, meters per second squared. That's the units of the Newton. So let's look at newtons in terms of converting mass to weight. In this situation, we have an object that weighs 1 kilogram. We know that the conversion of 1 kilogram to newtons is roughly 10 newtons. This is because of the force of gravity. We know that gravity accelerates objects at a rate of 9.81 meters per second squared. This is rounded roughly to 10 for the sake of easier calculations. So we'll look at a sample problem. We have this box that weighs 4 kilograms. How much force does the block exert on the ground? So essentially we're looking for the block's weight in newtons. Well, we have 4 kilograms. We know that 1 kilogram will be 10 newtons, so that's 10 newtons per kilogram. We can cancel out the units and do this conversion to find that the block weighs 40 newtons. That's how much force it exerts on the ground. There are 2 different types of forces, contact forces and field forces. Contact forces are those that act on objects as they touch one another. Here are some examples of contact forces. We have a person pulling a wagon. The person is touching the wagon as he pulls it along, and that's what's causing the wagon to move. That makes this a contact force. Some other examples are a person's foot kicking a ball or a foot stomping on a floor. Both of these forces are contact in that the 2 objects touch one another as they cause each other to accelerate. The other type of force is a field force. This is a force that occurs from a distance on objects that are not in contact with one another. An example of a field force is the force of gravity, which is everywhere on the Earth. Gravity does not occur because of contact between 2 objects. It is a force that exists everywhere on the surface of the Earth. Let's look at a basic structure for modeling changes in motion as a result of forces. All forces can be modeled using free body diagrams, or FBDs for abbreviation. These are diagrams that represent forces as vectors and show how they act upon an object. Here are some basic guidelines for drawing FBDs. Number 1, treat forces as vectors. We learned about vectors in the last chapter. Vectors express the magnitude and direction of the force. So those are the 2 aspects that a free body diagram will express. We want to start every force problem with an FBD. This will make it easier to visualize the different forces that are acting on the object in the problem. Finally, for the purpose of AS physics, we're going to disregard the size and shape of the object. So no matter the shape of the object and no matter where the forces are applied, we're going to treat the object as a point, where the forces are applied to the center of the point. Here's how to draw an FBD. First, choose a coordinate system with an object at the center. If we have this red box here, we want to place our red box at the center of the coordinate system. Then we can draw a horizontal axis and a vertical axis around the box, with the box as the origin. Second, we'll compute all angles with respect to the positive x-axis. If there's a force pushing this way on the box, we'll measure the angle theta with respect to the axis on the positive x side. Finally, we get the sum of force components in each direction and set them equal to 0. This will represent balanced force on an object. So this will require using vector components as we did in the last chapter. For instance, on this blue force, we have an x component in this direction and a y component in this direction. Breaking down the forces in components will help us in our calculations later on. So let's practice some free body diagrams with an example. This is an object that's at rest. We want to solve for its weight and for the force x, which is pulling up on the left side over here. So we'll start by setting forces equal to each other in the x direction. We know that there are two forces with x components. There's this x component over on the left side, and the x component of this force on the right side. These forces must be equal to one another for the object to remain at rest. So let's do some calculations. Sum of forces in the x direction will equal 20 cosine 25 degrees, that's the force on the right side, plus x cosine 135 degrees. That's the angle that this force makes with the x-axis. Now we know that the object is rest, these are all going to equal 0. So let's plug in some numbers. We have 20 cosine 25 degrees, that's about 18.1. We have negative 0.71, that's cosine of 135 degrees, times x equals 0. Now we can move this to the other side. We get 18.1 equals 0.71x. Divide by 0.71. We get that force x equals 25.6 newtons. That's how much is pulling up over here on the left side. Now let's solve for the weight of the object. This time we want to sum the forces in the y direction. I'll do that over here in blue. Sum of the forces in the y direction. Alright, we know that all of three of the forces have y components because we can see that each vector points away from the x-axis a certain amount in the vertical direction. So let's look at the angles they form. We have this first force, 20 times sine 25 degrees. That'll give us the y component. For the second force, we just solved for x. It's 25.6. We have 25.6 sine of 135. That's the angle the force forms. Finally, we have w for weight times sine of 270 degrees. That's the angle that this force forms with the positive x-axis. So now let's simplify. We know that this will all equal 0. We also know that the sine of 270 degrees is negative 1. This allows us to move the w over to this side. So now we know that w will equal 20 sine of 25 degrees plus 25.6 sine 135 degrees. I plug this all into the calculator to find that w equals 26.6 newtons. That's how much the object weighs, and we solved that all using an FBD. So let's do some practice. A truck is pulling a trailer down the road. Draw free body diagrams for the truck and for the trailer. So this problem is asking us to draw an FBD for each object in the situation. Let's look at the trailer first. The trailer is behind the truck. We'll represent it as a dot. The trailer has a certain weight that's pushing downwards into the earth. We also know that since the trailer isn't actually traveling downwards, the earth must be exerting an upward force on the trailer of equal magnitude. So that balances. We'll call this weight, and we'll call this U for now, for upward force. We'll go into that more in depth later in this chapter. We also see the pulley that's causing the trailer to move forward. That's attached to the truck. We'll call that T for tension, because tension in the pulley is causing the trailer to be pulled forward. So those are the forces on the trailer. Now let's look at the truck. We'll represent the truck as a second dot. The truck has weight, just as the trailer does, and it also has an upward force that's balancing out the weight to keep it level on the surface of the earth. Once again, we'll call this weight, and this is the upward force that we'll learn more about later. Finally, the tension in the pulley is also on the truck. However, it's moving backwards because the pulley is behind the truck. Those are the forces acting on the truck.